We are given the graph of a function, and the question asks us to state the numbers at which the function is discontinuous and explain the reason for each discontinuity. So I'd like to start by tracing the graph and really pay attention to where I need to lift my pen from the paper. Because anytime I lift my pen, I know there's a discontinuity right there. Let's go. Tracing the graph. I need to lift my pen right here and jump up to the next segment of the graph. So I know there must be a discontinuity at -2. Continue. Tracing the graph. I need to lift my pen right here in order to jump over the hole to get to the next segment. So I know there must be a discontinuity at the hole, which happens at x equals 1. Continue. Tracing the graph. I need to lift my pen right here, jump down to this point, and then jump back up to the next segment. So I know there must be a discontinuity at 4. Continue. Tracing the graph. And the arrow here just means the graph is going to keep going up forever. So the graph is going to keep going up forever. However, eventually we have to lift our pen in order to jump down to the next segment. So I know there must be a discontinuity at 6. So there. In total, we have 4 discontinuities at x equals -2, 1, 4, and 6. Now, I'm going to explain the reason for each discontinuity. But before I do that, let's do a quick review on one critical requirement for a function to be continuous at a certain number. In order for a function to be continuous at a number a, one condition must be met. If we take the limit of the function as x approaches a from the negative direction, must be equal to the limit of the function as x approaches a from the positive direction. And lastly, must also be equal to the value of the function at x equals a. In case you find this concept to be a bit too abstract to grasp, I'm going to throw in some numbers to help you visualize the meaning of this statement. So let's say we want a function to be continuous at x equals 5. Now, what are the ingredients we must have? Well, we must make sure that as the function approaches 5 from both directions, the function must be approaching the same value. See, if a function approaches different values coming from the left and from the right, then we know there must be a discontinuity at 5, right? So in order for a function to be continuous at 5, we must make sure that the function approaches the same value coming from the left and from the right. Now, let's define continuity in terms of limits. If we take the limit of the function f of x as x approaches 5 from the negative direction, and say our function gets closer and closer to the value, say 3. Now, in order for the function to be continuous at 5, we must make sure that if we take the limit of f of x as x approaches 5 from the positive direction, so approaching 5 from the positive direction, the function must also get closer and closer to the value 3. However, having these two limits equal to each other is still not enough to guarantee that the function is continuous at 5. Because as we can see from the graph, there is still a tiny little gap between the left curve and the right curve. And therefore, we must define the function at 5 to also have the value 3 to fill in the gap. And there, only when we have all 3 arguments equal to each other, then we can guarantee that the function is continuous at 5. In other words, if we do not have all 3 arguments equal to each other, that simply tells us we have a discontinuity. Cool. So now we are ready to explain the reason for each discontinuity in this graph. For each discontinuity, let's quickly list out all 3 arguments. And we should expect the 3 arguments not all equal to each other. For example, we might have 2 of them equal, but not all, and therefore the reason for having a discontinuity at a particular number. Let's start with the discontinuity at x equals -2. Approaching -2 from the negative direction. So approaching -2 from the negative direction, the function gets closer and closer to the value 3. Next, approaching -2 from the positive direction. Approaching -2 from the positive direction, the function gets closer and closer to the value 5. Next, the value of the function at -2, at x equals -2, well, at x equals -2, is the function defined here? No. See, here we have an empty hole, right? So the function is not defined there. However, is the function defined right here? Yes, because here we see a solid dot indicating the function is defined right there. Okay? So the value of the function at -2 is equal to, right here, 5. Now, look at the 3 arguments. Are they all equal to each other? No. Well, we have these 2 equal to each other, but not this guy. And therefore, we must have a discontinuity at -2. And since the function jumps from one value to another, see, in this case, the function jumps from the value 3, jump up to the value 5. This type of discontinuities are called jump discontinuities. Jump discontinuities. Now, let's look at the discontinuity at x equals 1. Approaching 1 from the negative direction. So approaching 1 from the negative direction, the function gets closer and closer to the value 2. Next, approaching 1 from the positive direction. So approaching 1 from the positive direction, the function gets closer and closer to the value 2 as well. And next, the value of the function at 1. So at x equals 1, is the function defined here? No. See, here we have an empty hole, which indicates that the function is not defined there. Right? In fact, is the function defined anywhere on the graph at x equals 1? No. And therefore, the value of the function at 1 is not defined. Now, let's take a look at the 3 arguments. Are they all equal to each other? No. See, the value of the function at 1 is not equal to the limit of the function approaching 1 from either side, right? And therefore, we must have a discontinuity at x equals 1. Interestingly, this type of discontinuities also has a name. They are called removable discontinuities. Removable discontinuities. removable discontinuities, because we could remove the discontinuity by simply redefining the function at 1 to be equal to 2. And that way, we can fill the hole and the function becomes continuous at x equals 1. Now, let's look at the discontinuity at x equals 4. Approaching 4 from the negative direction. Approaching 4 from the negative direction, the function gets closer and closer to the value -3. Next, approaching 4 from the positive direction. So approaching 4 from the positive direction, the function gets closer and closer to the value -3 as well. Next, the value of the function at 4, so at x equals 4, is the function defined here? No. See, here we have an empty hole. See, empty means the function is not defined there. In fact, the function is defined right here. See, here we have a solid dot, right? Solid dot. Solid means the function is defined right there. Right? Cool. So, the value of the function at 4 is equal to -5. Now, take a look at the 3 arguments. Are they all equal to each other? No. Once again, the value of the function at 4 is not equal to the limit of the function approaching 4 from either side. And therefore, we must have a discontinuity at x equals 4. Here's a question for you. What type of discontinuity do we have here? It's a removable discontinuity, because we could remove the discontinuity here by simply redefining the function to here. See, if we could redefine the function at 4 to be equal to -3. And that way, we could fill the hole and the function becomes continuous at x equals 4. Now, let's look at the discontinuity at x equals 6. Approaching 6 from the negative direction. So approaching 6 from the negative direction, the function gets closer and closer to, the arrow here tells us that the function will keep going up forever and eventually approach positive infinity, right? So positive infinity. Next, approaching 6 from the positive direction. Approaching 6 from the positive direction, the function gets closer and closer to the value -1. Next, the value of the function at 6. The value of the function at 6 is defined right here at this solid dot, right? Yeah. So the value of the function at x equals 6 is equal to -1. And once again, let's take a look at the 3 arguments. Are they all equal to each other? No. In this case, these 2 are equal, but not the first guy, right? And therefore, we must have a discontinuity at x equals 6. Now, I want you guys to take a guess at the name for this type of discontinuities. They are called infinite discontinuities. Infinite discontinuities. Because anytime we see the left limit or the right limit, or both, being infinite, we know we have a infinite discontinuity. Cool. So in conclusion, At x equals negative 2, the function has a jump discontinuity. At x equals 1, the function has a removable discontinuity. At x equals 4, the function has a removable discontinuity. And lastly, at x equals 6, the function has a infinite discontinuity.
Right, that's all for today's sharing. I do hope that my sharing will help you to improve your additional maths, especially the limits from the differentiation topic. Till then, I shall see you in my next video sharing lesson. Bye bye and have a nice day.